Welcome to Maths for All. I'm Aisling Flynn. This is Calculus 1.1, the derivative. Calculus. Calculus is considered the mathematics of moving things. Calculus describes how something is changing. For example, the position of a moving object. How quickly is it changing? And this gives us speed. Or a population. How quickly is it changing? Is it rising or falling? And we get the growth rate or the rate of decline. Slope. So when we take data for things like the motion of an object or the population of a city, we can put that data onto a graph to visualize the changes. And as a result, we get a line or a curve. And we can measure the changes in motion or population by studying the slope of the line. The slope or gradient of a line is a measure of its steepness. So how quickly is the line rising or falling? And to measure it, we would study the vertical change against the horizontal change. So the slope is given by vertical change over horizontal change when you compare these two. So if we look to the red line on the right and we choose any 2 points on this red line, so I'm going to mark it with an X down here at the bottom, and further up I'm intentionally choosing points on the red line that cross through grid lines. Okay, so I've chosen 2 points on that red line, and I'm going to study how do you get from one to the next. Okay, so let's run horizontally. So I'm using this yellow line here to run horizontally from the first point, and we always work from left to right until I'm directly under the second point. And this is my horizontal change. Okay, and then let's look at the vertical change from one point to the next. I'll just write vertical there. Okay, and we have other names and symbols for this horizontal and vertical changes. Sometimes the horizontal change is called the run, so you run across, and the vertical change is called the rise, so you rise up. Indeed, sometimes the vertical change goes downwards, so it can fall also. Other symbols that you use to describe these would be delta x for horizontal. That means the change in the x direction, using x as your horizontal axis, and delta y as your vertical change, or the difference in the y direction. Okay, so for this particular red line, now let's calculate the slope. Slope equals, alright, so let's measure the rise, or how far up or down you must go from one point to the next. So I'm using each grid square as a unit, so 1, 2, 3, 4, 5, 6, so 6 units in difference between one point and the next. And let's measure the run then in the horizontal direction. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and so my slope is 6 over 8, or if you want to simplify that, 3 over 4, 3/4. Or if you want to change that to a decimal, you get 0.75. Now what does that mean? It means for every unit in the horizontal direction you go, so if you go across 1 unit, you should rise up 0.75 of a unit to remain on your line, and that gives us the slope of the line. Okay, if the x axis was to represent years, okay, and the y-axis was to represent population, let's say by 1,000 of a little town. It would say that every year that passes, the population increases by 0.75 by 1,000 by 750 people. Okay, so more about slopes, and we're going to calculate the slopes from the following graph. Okay, we have 4 lines here, and for each one we're going to use our rise over run. So line number 1 is the red line. So again, choose any 2 points, but it's useful to choose 2 points that are on grid lines. So I'm going to choose this one here, marking it with an X, and the next one over, and I can draw horizontal and vertical lines. You get a little right angle triangle. So I'm going to say that slope 1 equals rise over run. So if I run across 2 boxes, I have to rise up 1. So we get a slope of a half, 0.5. And you can see that that red line is rising, but it's rising gently, or not too quickly. Let's compare that now to the green line, line number 2. Again, let's find 2 points that are on grid lines. So there's one down here right at the very bottom, and the next one I see crossing a grid line is here. So again, construct your horizontal and your vertical. So that's 1, 2, 3, 4 units across. So the slope of line 2, which is rise over run, has a run of 4 and a rise of 1, 2, 3, 3. So that one has a slightly greater slope of 0.75. So you can see there clearly that the green line is rising more quickly than the red line. Now let's look at line number 3, which is purple or perhaps navy in color. Okay, again we have to try and find 2 points, ideally 2 that are on a grid line. Now I'm just going to delete some of my markings from earlier so we can see more clearly. Okay, so I can see a point here on the x-axis and one here on the y-axis, and I'm going to construct a right angle triangle. Now to run across, this time we're going backwards. Okay, so that tells me something in itself, and we have to come down and not up to go from one point to the next. Okay, so this time my rise is in fact a fall. It's going down 1, 2, 3, 4 units, and my run is 3. Okay, so the slope of line 3 is rise over run. Now how to signify that that line is actually falling as you come from left to right? We give it -4 for the rise, and the run was 3. So in decimal that's -1.3, and it recurs, so we'll put a little dot on top of that, 1.333. So the minus signifies a negative slope, and it shows a line that is falling. And let's compare that with another falling line of line 4. Okay, let's take some points of interest on line 4. And that is the turquoise line. There's a point on a grid line, and there's a point. So if we fall 3 and run 2, okay, I get -3 over 2, which is -1.5. So this is a negative slope showing that line 4 is falling. But one fine 0.5 is bigger in magnitude than 1.3, so it is falling more quickly than line 3. Okay, what about the slope of a curve? The slope of a curve is different at different parts of the curve. So let's look at this diagram. So the curve comes down to a minimum point, so there we've got a minimum, and then it increases again. Okay, so let's take that point of minimum and let's look to the left and to the right of it. So left of minimum, we've chosen a single point here where x is -2, and we've drawn a tangent. Okay, so that red line that touches the curve at the point where x is -2 is called a tangent, and what it does, it shows the slope right at that point of contact. So if you were to zoom in and zoom in to where x is exactly equal to -2, the slope of the curve would be equal to the slope of that tangent. And here you can see that the red line is falling as you go from left to right, so it has a negative slope, and it has been calculated there for us. It says slope equals -5, so it's falling. Okay, then the curve comes around. If we move past the minimum and over to the right hand side where we have this green line, and which is a tangent to the curve when x is equal to 1. And now you see that the slope has changed from falling to climbing or rising, and now the tangent at that point has slope of 7, so +7. And if you continue up the curve to where x is 4, the tangent at that point has slope equals +19, so it's rising very rapidly. Okay, so couple of points there. The slope of a curve changes as you go from left to right. Also, a tangent to the point that you're studying gives the slope of the curve right at that point. It's called the instantaneous slope. We'll talk about that later. And there you have it. And we'll also talk about the slope at the minimum point later on. So here's another example of a function. Okay, it's an exponential function. Starts off with they're all positive slopes, but starts off with a very gentle slope of 1, and then begins to rise more quickly, slope of 5, and rise more quickly again, slope of 10. And here we have a picture of another curve with many turning points, and you can see here of the changing slopes. Okay, in particular I want you to look at the minimum or the lowest point here, which is called a turning point. It is when the slope changes from being negative to positive, and it happens again up here at the very top. This one here is called a maximum. Okay, and where the curve takes a turn, so it goes up at the maximum, it's going from being positive slope, so rising, to falling, negative slope. And a key point of information that you'll use later on is that the slope of a tangent at a turning point will be 0. Why? Because the tangent touching at that point is completely horizontal or flat, and it has no slope. Instantaneous rate of change. So this is what the word suggests. At an instant, what is the rate of change? So at a single moment in time, if you pause or stop the stopwatch, or if you look at a single point on a curve, what is the rate of change? So we get to the instantaneous rate of change through a process. So let's look at the first diagram on the left, and look at the red curve. If we wanted to find the slope or the instantaneous rate of change at a single point on the curve, we're going to start here by examining the slope between points A and, let's call this point B. Okay, so this blue line approximates the curve, and the slope is given, of course, by our rise over run, delta y over delta x. So what we hope to do mathematically in the next lesson is to bring that closer to an instant. So make that blue line shorter and shorter. So here you can see in diagram 2 that the blue line has gotten shorter. Point B is getting closer to point A, and the slope, while still being delta y over delta x is smaller, getting smaller, okay, and getting closer to 0, and the slope, the blue line, is getting closer to the red curve. Okay, it's getting to be a better and better approximation. And in the third diagram you can see it's even better again. It's nearly almost matching. The blue line is nearly almost matching the red curve. And when B becomes point A, so when delta x becomes 0, that's when you get the slope at an instant, at a single point. So we'll be doing that mathematically in the next lesson. As delta x gets smaller, we get closer to the instantaneous rate of change. And delta y over delta x becomes something called dy dx. We'll talk about that in a second. As delta x approaches 0, so as delta x gets closer and closer to 0. And this dy dx, we'll use that in the next lesson, is called the derivative. And it is equal to the instantaneous slope. And that's what we'll be using calculus to find over and over again in the next few lessons. By any other name, so I've talked a lot about slope. I've just introduced dy dx, which I call the derivative. So there's a few terms which all mean the same thing. Okay, dy dx is the derivative or the slope of y, whatever y is. So if you were given, I'll just backtrack there, the equation of a line 2x plus 5, something like that, dy dx is the slope. Okay, and I can tell you now, and we'll look at that in the next lesson, that the slope of that line is 2. Okay, the other way it can be written is if you're using function notation. So if your function f of x is equal to 2x plus 5, it describes a straight line on a graph, and f dash of x, the slope of this line we've just seen, is 2. So this dash means the derivative. It can be called instantaneous rate of change. It can be called the slope, or it can be called the derivative. Okay, but all the same thing. Now, you do it. Check you've understood the lesson by doing your quiz, Calculus 1.1, and practice what you've learned by doing your written exercises.